This video is going to cover rigid body equilibrium. Rigid body equilibrium is statics, and in statics we effectively solve everything with our three equations. Some of the forces in the x, some of the forces in the y, and some of the moments, about a point. Doesn't really matter which point, but a point. Those are our three equations that we get to pretty much solve everything. So in order to do this, hopefully it's just an easy member, but if it's not, you can always make cuts, break things down, and do it again. But effectively it's the rigid body, so we're looking at the outside of all of the members. So in this example, we just want to find our reaction forces at A and B. B is a roller, so he just has a By force. A is a pin, so he'll have an Ay and an Ax force. And we have four 11 kilonewton loads placed along our beam spaced 3 meters apart. And then lastly, we have this 8 kilonewton force at an angle of 60 degrees. So step one is probably good to kind of break our 8 kilonewton force up into a horizontal and a vertical component. Right, and remember he is going to act at that point there on the end. So because the cosine that we have here, because this angle we have here is touching the horizontal, this is going to be 8 times cosine of 60, because remember cosine is the adjacent over the hypotenuse. So the 8 kilonewtons is the hypotenuse, the adjacent here is this horizontal member. So 8 times cosine of 60 is our horizontal component, which means our vertical is 8 times the sine of 60 degrees for our vertical component. Now that we have that, what can we start off by doing? If we sum the forces in the y direction, we have two unknowns, not really good. We can sum the forces in the x direction. That's perfectly fine. So we'll sum the forces in the x direction and set it equal to 0. We have Ax, and we also have our 8 cosine of 60 degrees force, so therefore our Ax is going to be equal to negative, this is 4.00 kilonewtons. So that was pretty simple. Again, you can't go on to summing the forces in the y because we don't have one of them. We have one equation, sum the forces in the y, and two unknowns. So that's no good, so we're going to instead sum the moments, as that's our only other option. And we're going to sum the moments about a point to try and reduce as many things acting unknown-wise on our member. So I'm going to sum about A, because if I sum about point A over here, I'm going to remove both Ax and Ay. So even if you didn't know Ax, you could still do this. So we're going to sum the moments about A, set it equal to 0. I always take counterclockwise to be positive. And remember that a moment is a force times a distance. Force times a distance. That is what a moment is. So when we're looking at the force Ay, who would create a moment about A, but his distance to A is 0, so he doesn't create a moment at A. Ax would create a moment about A, but the distance to A is 0, so he does not actually create a moment. So do be careful when you're doing that. If you were to take a moment about B, remember that this 11 kilonewton force would also be acting at B as well as By. So just be careful when you're taking moments that you are including the distance for everything. So we're going to start at A and kind of work our way to the right and see what we've got. First up, we've got this 11 kilonewton load, and that 11 kilonewton load is going to be going our negative direction. So negative 11 times his distance to A of 3 meters. Then we have our next 11 kilonewton load here, and his distance is going to be 3 plus 3, which is 6. Then moving on over, we have another 11 kilonewton load, so minus 11 times his distance of 3 plus 3 plus 3, which is 9. Then we have By. By is at the same spot, but he's going opposite, and he's going to be creating a positive moment. By over here going to be rotating this direction, which is positive. So positive again, this is By, we don't know him, times his distance of 3 plus 3 plus 3, which is 9. Then we have our last 11 kilonewton load. So again, minus 11 times a distance of 3 times 4 is 12. And then don't forget we do actually have that 8 kilonewton force. Now the horizontal component here acts in line all the way back to A. So his distance is 0. The distance perpendicular from him to A would be 0. So again, he's not acting, but the perpendicular distance from the vertical component back to A is a real thing. So we have, again, he's going the same direction as everybody else, so minus 8 times the sine of 60 degrees times his distance of 3 times 5 is 15. So blah, 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 we've got By in there, only By, only unknown, so By is going to be equal to 48.2 kilonewtons. That's massive. Really, really massive. So now that we have him, we can go ahead and sum the forces in the y direction and set it equal to 0. We got Ay going up. We've got minus 11, minus 11, minus 11, minus 11. There's 411 kilonewton loads at the top. Plus we've got By. We said By was 48.2. And then we have our minus 8 times the sine of 60 in there. So we can find Ay, and Ay is going to equal 2.73 kilonewtons. Rather small because By has taken the grand majority of it. So anyway, that's rigid body equilibrium. It's just straight up some of the forces in the x, some of the forces in the y, and some of the moments. Remember that a moment is a force times a perpendicular distance.